So, okay, let's start. Welcome to lesson number 7 on Stoechiometric Organometallics. Subject of today's lecture is Regioselective deprotonation of carbonyl compounds. Well, if we have a ketone like this, let's call it the starting material A, and we treat it with potassium T-butoxide. Usually that is done, or often this is done, in tertiary butanol as a solvent. And we use elevated temperatures. Then we will get a potassium enolate, predominantly this one with the double bond located here, the higher substituted double bond, and therefore thermodynamically favored. So the substituents help to allocate the anionic charge of the enolate just by inductive effects. On the other hand, if we use LDA as a base, THF as a solvent, and low temperatures, minus 78 degrees, then we will get to the enolate, in this case, of course, a lithium enolate with a terminal double bond. This is thermodynamically less favored, but obviously then kinetically favored under reaction conditions. So let's call this product C, and this reactive intermediate for further reactions then B. If we visualize the difference between thermodynamically and kinetically favored in a diagram where we have the energy here and the reaction coordinate there, well, we would start at a certain energy level, the energy level of the starting material A. At far lower energy level, we will have B as the thermodynamically favored one, and a bit above C. So, to get to B, we have to cross an energy barrier. This is the activation energy from here to there. Here we have a transition state. And since C is the product that is obviously kinetically favored under these reaction conditions, we can assume that we have to cross a significantly lower energy barrier to get to C than to B. Okay, this simply means, well, we usually get faster to C than we get to B because we have to cross a higher energy barrier. Well, what makes this product kinetically favored? Simply, as main reason, steric hindrance. The steric hindrance that is higher at this position by the additional substituent here compared to the steric hindrance at the terminal methyl group. And if we have a sterically hindered base, it can of course attack a hydrogen here at the terminal methyl group better and faster compared to this position. While on the other hand, this base, the potassium T-butoxide, is also a somewhat sterically hindered base. But we operate in this case at higher temperature. And at higher temperature, well, we have enough energy in our reaction flask that we can easily get across that somewhat higher energy barrier. Well, what would happen if we use a very small base, potassium or sodium methanolate, for instance? Then it wouldn't make much of a difference getting to product type C or getting to product type B. If we have a small base, then well, the difference in energy barrier is much smaller. So by using a real sterically hindered base like LDA, going to low temperatures and using rather short reaction times, we can secure that we have at the end preferentially the kinetically favored product. Higher reaction temperatures, longer reaction times, that the equilibrium can be formed. Well, this would of course favor then the thermodynamically favored product. An interesting example is this one. Deprotonation here at the benzylic position is of course thermodynamically preferred, since we would get a conjugated enolate conjugated to the phenyl group. But if we again use LDA at low temperature, sterically hindered base, this position is especially shielded by the phenyl group. Therefore, kinetically favored is the deprotonation here. It has been tested under these reaction conditions. We get a mixture but it's a 99-to-1 mixture. So LDA indeed is very selective in this case. Well, how did these guys figure out that they had this ratio? So they trapped the enolates simply by adding acetic anhydride. So then the enolate attacks as a nucleophile at the carbonyl group of acetic acid anhydride, and it is a simple addition-elimination process which leads us to the enol ester. 99 to 1. So, and well, by NMR spectroscopy or maybe by GC, you can then determine the product ratio. Very nice example which illustrates that you can sometimes determine the outcome of a reaction by adjusting the reaction conditions, keeping in mind what we have learned before, is this one. If we choose potassium T-butoxide, higher temperature tertiary butanol, we should get a reaction which has the thermodynamically favored enolate as the predominantly one. And this means deprotonation here, the enolate. Here is the nucleophilic carbon center that intramolecularly attacks the C bromide. CC bond formation between this and this center. 1, 2, 3, 4, 5. A 5-membered ring is formed. Resulting in this product. The reaction has been done several times, but always with success of 86 to 94% yield. It is the cis-fused system because the transfused system would be rather strained in this case. Now you can guess what will be the result if we use LDA THF minus 78 degrees. In this case, preferentially, the kinetically favored enolate should be our reactive intermediate. This means deprotonation here, this enolate, and then CC bond formation from this position to that position, giving a 7-membered ring. This is indeed the case. 77 to 84%, but as a mixture of stereoisomers. In the literature about transformations with steroids, you find rather often this type of example. So here the 6-membered and another 5-membered ring for the steroid framework, deprotonating this alpha beta unsaturated ketone. We have two positions where we can deprotonate, here and here. These are the acidic positions, and so same reaction conditions as here. Thermodynamic control with potassium dibutoxide at elevated temperature gives the linearly conjugated system. And on the other hand, with LDA, again THF minus 78 degrees, we will deprotonate here to get the cross-conjugated lithium enolate. Next example, crossed aldol reaction. Mainly aldol addition, but well, what I'm going to say is also significant for aldol condensation reactions. Maybe we have a synthesis problem that we would like to perform a crossed aldol addition reaction of, this ketone with this aldehyde to get to this aldol addition product. How should we perform, or how should we choose the reaction conditions that we can achieve that? We have a problem. Well, this should be A, this may be B, and this we call C in this case. For instance, if we just mix A and B in our reaction flask, add a base, for instance, potassium hydroxide or sodium ethanolate, and a suitable solvent, what would happen? Well, the base will certainly deprotonate preferentially at the most acidic position. And aldehydes are more acidic than ketones. So this is the position that will be deprotonated. Then we have preferentially this enolate, and with this enolate we just don't get to this product. Moreover, this aldehyde has also the higher carbonyl activity. This carbonyl group is more reactive than this one. And that means that this enolate will preferentially react with the aldehyde. And we will get the homo coupling product. Later on, after all the aldehyde has reacted, yeah, then the ketone will start to react. So we will get a mixture of products. Well, what can we do to get to this product? Well, obviously we should not mix A and B together. We should use A exclusively for deprotonating with LDA at lower temperature. Again, maybe minus 78 degrees. And we will get to the kinetically favored enolate. And if we then add the aldehyde B, still at low temperatures, and later on, secondly, perform a hydrolysis, of course, hydrolyzing under very moderate reaction conditions, very cautiously acidifying, because otherwise we would get aldol condensation. Then we will get C. Well, and this has been done, and you will find in literature that a 60% yield of C was achieved. This is not bad for this reaction. On the other hand, we can think about, well, what happened to the other 40%? Always a question we should ask. Of course, this enolate is also a rather strong base. And instead of reacting as a nucleophile, it can also react as a base and then deprotonate to some extent B, getting the competing reaction. That's the main reason why we can't get above about 60%. A similar reaction this time an alpha-beta unsaturated ketone, aldeA, same reaction conditions. Kinetically favored the similar enolate. This enolate is called the cross-conjugated one. Instead of the linear conjugated enolate, if we deprotonate here at the terminal position, this here, we would get the linear conjugated one. Plus, now plus the aldehyde, again, alpha-beta unsaturated one, and indeed it works. Getting finally, after hydrolysis, a 70% yield of this aldol addition product. While for me it's somewhat astonishing that we achieve still a good yield, because in this case we also have another competing reaction, a Michael type addition process where the enolate reacts at the better position. However, this was found as the main product. But 60 to 70% yield seems to be the maximum we can achieve here. But this has been improved by Mukayama. So, more than 40 years we know the Mukayama aldol addition reaction. In this case, for the Mukayama aldol process, we also deprotonate, for instance, with ketone, cyclohexanone, low temperature, for instance, in THF, getting the enolate, and then trapping it, for instance, with trimethylsilyl chloride. And isolating, for instance, by distillation, the TMS enolate of the cyclohexanone. This is rather stable under neutral and basic conditions, so we can store that and we can apply it for the Mukayama aldol process. And this is adding an aldehyde. Here's an example, simply benzaldehyde. The reaction is usually done in dichloromethane at low temperatures, minus 78 degrees. We need a catalyst, a Lewis acidic catalyst, for instance, titanium tetrachloride. It activates the electrophilicity of the carbonyl group. CC bond formation takes place, and a final transmetallation, exchanging the titanium by the silyl group, finally leads to the aldol addition product protected by the TMS group. And rather often one can achieve yields above 90% for the Mukayama aldol process, and in this case a 92% yield was reported. Another more sophisticated example for a Mukayama aldol reaction reported from David Evans' lab in Journal of the American Chemical Society in the year 2000. Page 10,033. Here we have the aldehyde. Now we need the enol, the TMS enol ether. In this case, it's a special one with a thiol group here. So it is the TMS enolate of a thioester. It is applied in small excess. Once again, dichloromethane minus 78 degrees. And now a more sophisticated catalyst based on tin triflate with a chiral bidentate ligand. %, of this chiral Lewis acid is applied. Giving the Mukayama aldol product. This one, enantioselectively. So yield again above 91% and an enantiomeric excess of 94%, which is quite good. Well, let's go on with some problems which you please try to solve as exercise. First problem. This is the starting material. And the question is, how can we get from this starting material to this product? Well, it's a bit tricky. I did not forget the ethoxy group in this drawing. Yeah. So it's a bit tricky. Please think about how would you solve this synthesis problem. Well, some of you have indeed found the solution to this problem. So, first of all, it looks like that we have to activate this position, deprotonate here, and then to alkylate there. Well, however, then it's the question, how can we get rid of the methoxy group? This would be a problem. So, but we can use the trick. So the solution to the problem is, first step is LDA, deprotonating with LDA, again, usually THF minus 78 degrees. So, and under these reaction conditions, we will get the kinetically favored enolate, and this is the cross-conjugated one. We need a 3-carbon electrophile, allylic bromide. Should work best. CC connection from here to this. Well, maybe it will undergo an SN2' reaction with the nucleophile attacks at this position, but the result is all the same, of course. Well, how to get from here to there looks even more complicated, but is rather easy. This has to change to the ketone, and we have to get rid of this one. Well, we simply need to change the oxidation state. Reduction. For instance, with lithium aluminum hydride. So, and this partial structure, what is that? Well, this is an enol ether of a beta hydroxy carbonyl, beta hydroxy ketone, so an aldol system. What we need is an aldol condensation then here, simply by hydrolysis under acidic reaction conditions. So protonating here is a leaving group and so on. This will lead to this structure, and if you compare it, well, it's the same like this. Next exercise. Now the question is, starting from this well-known and very cheap starting material, acetoacetic acid, ester. How do we get to this derivative elongated at this position? Please try to figure out an idea for that. So first idea should of course be treating this with LDA at low temperature, while hoping for the deprotonation here. Unfortunately, this CH2 group is double activated by the carbonyl groups. It's far more acidic than the terminal CH3 group, and while even with a sterically very hindered base, it will always be deprotonated here, just because we have then a conjugated enolate, a donator-acceptor stabilized system, moreover, with the lithium cation chelated here. All these factors stabilize this structure. Well, if you add now the electrophile, the allylic bromide, of course, an alkylation would take place here. Well, the solution to the problem is just add a second equivalent of LDA, then you will get the linearly conjugated system. And this position is the beta nucleophile compared to this position, because sterically less hindered, and at the same time the enolate, which is formed after alkylation here, is this one. Here you have the alkylation and it is the conjugated one. So it's also thermodynamically favored to let the alkylation undergo at this position. So adding allylic bromide, hydrolyzation will lead to this product. Last exercise for today. How can you transform this 3-ethyl cyclopentanone to this isomer? Please think about the problem. One additional hint for solving this problem. Please think about how would you synthesize the starting material and how would you synthesize the product if you would start from something. This will help. So clearly somehow disconnecting this CC bond and transforming the methyl group to this position, getting rid of a hydrogen there, is not possible. It's clear. Yeah? Well, but now thinking about how would you synthesize these. Alpha-beta unsaturated carbonyl compounds usually are synthesized by aldol condensation. So, retrosynthesis arrow. This product we would try to synthesize by intramolecular condensation of this diketone and here retrosynthetic analysis would lead us to this starting material. Well, I think it's clear both are the same. So, since the aldol condensation process is reversible under basic conditions, for instance, sodium hydroxide in water, well, you could just treat it, water or ethanol, under these basic conditions and wait until it reaches the equilibrium. And the equilibrium prefers this product because the olefin is higher substituted. Therefore, this is the thermodynamical preferred one. Well, presumably the yield of that in this transformation would not be a good one, since under reaction conditions you can have a lot of competing reactions, deprotonating here and Michael type addition processes and so on. But at least you would get some of that. But on the other hand, well, you wouldn't try to transform this to that, you would of course start with that and selectively trying to get to this one or that one. So thank you for listening for today. Tomorrow's lesson will have a subject enantioselectively deprotonating substrates. See you tomorrow.